It's more like the matter with the Zoom. Is a matter of with the Zoom. How's it called?
Okay.
Recording that if somebody is speaking very far from the laptop, the audio goes down.
You want to speak closer?
It doesn't really matter.
Okay.
Because almost nobody watches the video.
Okay. Okay, I think we can start. So good afternoon, everybody. My name is Ana Trindade Falcão. I'm here with Andrea, Frederico, Amy, and Caroline. We are the organizers of the head colloquium. So we are starting today with a talk by Andrea Sacchi. So he obtained his PhD at the University of Florence in 2022, and he has been working here at the CFA since April. And Andrea's interests and research revolve around tidal disruption events, AGN, and their accretion processes at large. And today he'll be talking about the X-ray puzzle in NGC 300. Welcome.
Thanks for the introduction. Hi, everybody. Today I will be talking about this work I've done while I was working in Pavia last year. And yep, there we go. Okay, and there's a huge list of collaborators because this was a very puzzling source, which has been. Yeah, well, you'll see. You'll see why. Okay, so let's start. Well, this is NGC 300, is an extremely well-studied galaxy. Why? Because it is face-on spiral. Well, it is beautiful, first of all. It is the closest one to the local group in the scattered group, at about 2 megaparsecs from us. And given the favorable inclination and position, it has been studied a ton. Furthermore, there exploded around here a ULX, NGC 300 X1, which has been studied a lot. So much that this is a stack image in the M2 band of U-Boat, a stack of 170 images I did personally, which was a pain. Let's go on. What is interesting for us today is this source, which is about 1.9 kiloparsecs from the galactic center of NGC 300. You can see there the contours are Chandra contours. And one of my collaborators thought it was fun to name this source after the Italian black widow, as there already exist sources named after the American and Australian black widows. And the vulgar name is Malmignata of this beast. So how was it discovered? Why? Why is it interesting? It was discovered because serendipitously, it has this pulsation in its X-ray signal. You can see it's a roughly 6-hour modulation with a pulse fraction of about 50%. It has been found with this survey of the Chandra ACES data, and the acronym is particularly fun, apparently. And you can see here the power spectrum of this source with the clear spike at around 6 hours with the detection threshold, and you can see here the folded spectrum. Okay, what does it looks like the spectrum of this source? Well, as you can see, is well, maybe you cannot see or you don't have the the taste, but to me this is a quasi super soft spectrum. What does it mean? It means that basically all the emission is between 0.7 and 2 kilo electron volt, and there's nothing else there. If you model it with a black body, you get a temperature of about 100 eV. There's quite a lot of absorption for this source, and the unabsorbed luminosity is pretty high. So at face value, this is in the ULX regime. Furthermore, there is this dip, which is extremely significant at about 1.13 kiloelectron volt, and we have no idea what that is. So we know of no transition there which can create it, but it's there. You cannot reproduce the spectrum without it. What else? Oh, interesting, long-term variability. As I mentioned, this beast lives in NGC 300, which has been monitored for ages. So this is the X-ray light curve. And as you can see, the vast majority are upper limits that ride with Swift. There's also some XMM ones. And these one here is the detection which made us find this source out. What else? What else? Here you see some Swift detections, and in particular, this Swift detection was followed by a detection also with Chandra. In another visit, it was detected some 2 days later, something like that. And I stress your attention on the fact that the closest known detection to this one is about 5 months earlier. And we can say that the variability of this source is more than 2 orders of magnitude during this period. The next one, the next significant one is with XMM, and the source has dropped for at least 1 order of magnitude. Anytime we detect it is about at the same level, but definitely it goes up and down. For example, here it's basically 1 order of magnitude below. We tried to follow the spectrum and see whether there is any evolution. And here you can see the 2 Chandra detections in black and red. And as the counts with Swift were too little to do spectroscopy on each observation, we merged them together, and you can see in green the merged XRT Swift observations. We cannot say much because the statistic is not so good, and because by 2020 the effective area of Chandra in the soft band where this source emits is non-existent, basically. So what I did was just to try and see if I could reproduce the spectra well just by freeing the normalization, and yes, I can. So this, although not conclusive, seems to suggest that the spectrum remains more or less the same. Okay. What about the optical counterpart? As I mentioned, we have a lot of UVOT data too. So here you can see the UVOT light curve and the compared with the X-ray light curve. And in particular, here is invocation of one of these Swift detection. You can see that basically there is in the X-ray upper limits before and after. And if you merge them, you get even deeper ones. Nothing in the light curve, no change in the magnitude in this band, nor in the others, nor in all the data we had. So what we did was to stack all the UVOT observations together and retrieve an SCD of this source in the optical UV band. This is the unabsorbed one, is well fitted by a black body, but of course you have to correct for the reddening. And how do you correct for the reddening? The least amount of reddening you can assume is just the foreground one, and you retrieve these values for the temperature and luminosity of the source, which are compatible with the blue supergiant. You can of course say, well, yeah, this is just the foreground. What about the reddening coming from NGC 300 itself? So you can correct more, and it's still compatible with the blue supergiant. But I said that the X-ray spectrum is heavily absorbed. So what if we correct with the full amount we retrieve from the X-ray spectroscopy? Well, you get this thing which is unphysical. No, nothing has this kind of SCD. So, okay, we really like the blue supergiant. Let's go with the blue supergiant. Actually, no, because we took a spectrum at the salt, and there are no individual stellar lines. What we see are just emission lines from the Balmer series, neutral helium, and some forbidden lines, which suggests that what we are seeing is a photoionized gas in an H2 region. So probably, so of course we can exclude that this is just a blue supergiant, and probably the correct amount of reddening to assume is something in between. And with these values, which are corresponding to our, let's say, reasonable upper limit on the reddening, makes compatible with a young stellar cluster, and the young stellar cluster emission would ionize the gas. This is about it for the thing we know about this source. Let me just go fastly through it. So it has bright X-ray emission, a 6 hours modulation in the X-ray signal. It is a transient source, and we can say that, well, let's turn it the other way around. We cannot exclude that it has a 5 months periodicity. 5 months is just derived by the distance between the two closest detections, and it cannot be excluded using the other upper limits we have. It has a quasi-super soft spectrum, as I said. There apparently is no correlation between the optical UV and X-ray emission, and is probably embedded in a young stellar cluster. Okay, what this is? Let's start with what probably it is not, such as a cataclysmic variable. We, at the beginning, thought about this, but we excluded it. Let's see why we thought about it. This source has a Gaia parallax. This source has a modulation, and this could be explained just by the orbital period of this object. Though the optical counterpart doesn't make much sense; it's too bluish. The non-correlation between the optical and X-ray, again, you would not expect this if it's a cataclysmic variable. The distance itself retrieved from the Gaia parallax doesn't make much sense. And the Gaia parallax accuracy is very poor, suggesting that this is just something like, okay, Gaia can retrieve parallaxes for quasars too, but that doesn't make much sense. Furthermore, the distance itself would put this source around 2 kiloparsecs from us, which, if you add the latitude to these sources is, would put it in the middle of nowhere, basically. So a cataclysmic variable in the middle of the empty space doesn't make much sense. So we can fairly say that, nah, this is not a cataclysmic variable. What it probably is, well, the easiest way to explain this source is just say this is a ULS, such as a subclass of ultraluminous X-ray sources exhibiting a super soft spectrum. This we like. It can explain the modulation. Again, this is a binary system with a black hole and a high mass star. So yes, this is just the orbital period. But if you say this, the only object we can fit in an orbit with a 6-hour period is a Wolf-Rayet star. And what did I say about the optical counterpart, that we can exclude a single object? Well, there's a way out. You say, well, you know, you have this Wolf-Rayet star embedded in a young stellar cluster. The emission from the old cluster can dilute the emission from the Wolf-Rayet. So, okay, we like this. The local absorption, well, these objects are famous for the winds, so it may very well be possible that there is some local absorption at that level. It can also explain. It makes sense that we see that deep because it has been observed in other sources too, other sources of this kind, for example, the one in M101. But what about the variability? these sources should be very close by, these two objects should be very close by one to another. Why do we see this kind of variability? One would expect to have a sort of constant emission. Well, you can try and say, well, maybe there's some kind of obscuration. You can say that, but then how can you explain the fact that we see no variability in their spectral shape? So this is at least a puzzle, and in this kind of object, you cannot explain the recurrency. That doesn't make any sense. So I guess this scenario deserves a big question mark, and we're gonna have to live with that. Our other scenario instead, and my boss is gonna laugh about this, because I find tidal disruption events wherever I look, is a tidal disruption event. Well, if this is a tidal disruption event, such as you had an object that got tidally disrupted by a black hole, then you have for free an explanation for the spectrum. These are thermal, these have thermal emission, and the variability. You would expect a ton of variability if this is the case. Furthermore, you can take whatever disk model you want and try and retrieve a value for the mass and for the mass accretion rate. And as you can see, it falls in the regime of intermediate mass black hole. But why is that banana shape cut? Well, first of all, why is it a banana shape? Because everything is very degenerate with the amount of absorption you have. But why is it cut? Well, because this source apparently lives in the very happy realm of not being able to be fit by any model we have. It is too heavy to be fitted with models built for solar mass black holes, and it is too light to be fitted well with models for AGN and supermassive black holes in general. So we have to live with that. We can say that this is sort of an upper limit of its mass. It could be lighter, but somewhere in that regime. How can you explain, though, the modulation of the signal? Well, you have several frequencies at the innermost stable orbit, circular orbit around a black hole. You have three basic frequencies which combines in creating the epicyclical length steering. Well, the orbital one is actually the orbital one. And as you can see over here, the values of mass and spin compatible with the frequency we observe in our signal, which is 6 hours. And as you can see, this band is the band of our mass, of the mass we will extract from the spectral fitting. So the only frequency which is compatible with both the mass we extract from the spectral fitting and from the frequency itself is the length steering one, but only if the black hole has basically no spin. So yes, you can explain it. You can explain the recurrency, assuming this is not just a one tidal disruption event, but the core survived, and so you have partial stripping anytime. Actually, I have put a reference here because this has been already invoked to explain another source. So okay, if you have a partial tidal disruption events, anytime these remaining stellar core will pass by the black hole, you get mass transfer, and so this brights up. Oop. Okay. What about the optical counterpart, though? Why there is no correlation between the X-ray and the optical counterpart? A spinless intermediate mass black hole? How do you create, well, an intermediate mass black hole of that mass, first of all? You can say, well, this is a young stellar cluster, maybe you have it, I don't know. This sounds a bit sketchy. And spinless, that amount of spin is basically non-existent. What? And the absorption feature that deep? You can sort of explain it when you have a puffed up disk with winds and etc. But with the slim disk that this interpretation considers, very hard to explain. So this source 2, this scenario 2 deserve a very well drawn question mark. So in conclusion, we have a strange beast, and we have two very problematic scenarios. Problematic because of different reasons, but problematic nonetheless. I cannot move this. Oh, okay, now I can move it. And how can we decide which one is the right one? Well, of course, you need more data, and especially more X-ray data, I'd say. So fingers crossed we'll get some more in the future, and we can say something more. But I'm happy to take your questions at this point. Actually, I'd be much rather to have your opinion about what these could be. Thank you so much for your attention.
Do we have any questions? Go ahead.
Yes. One when I saw a picture of the dip in the spectrum, I immediately thought cyclotron lines. I think that's interesting on board, and I think that goes with it's at least a linear in energy with magnetic field. That's something to note that. That would be amusing to work.
Yeah. I guess that could be an option, but I was working with somebody who was who did that. I'm not an expert in that. And I was working with somebody who was very well expert in that, and he didn't suggest it. So I guess there's some problems somewhere with that interpretation. We can discuss more and find out why he didn't consider this.
One of the things that you are seeing. It seems that there's not just one leak, but there are like more very big in the like around 0.8 from.
Yeah, the spectrum is quite noisy, but all the others are not significant. This was the only significant one, and it is well significant. All the others instead are just noise.
Second thing is like when we are talking about the tidal event with the intimate mass in that one, the mass that's we got to is actually 1.5 K. So how do you explain like a black hole with roughly 1,000 solar mass into the not in the like very core of the galaxy, now but it's like
with a lot of difficulties. That's how it is explained. There has been some efforts, some simulations actually, which can reproduce very heavy black holes in the center of clusters of this kind, but they assume a metallicity which is very off the one you expect for NGC 300. So it may be possible under very extreme circumstances, but it's very hard. Though, as I was showing, that banana was cut. So it is possible that actually there are some combination of other parameters that, for example, this inclination and such, that can lower the mass to a more reasonable value. It's kind of hard though.
And one thing like people usually look for is that the brother just around that region that can go in the same mass that or it's not like what that
yeah, exactly. The other source for which a partial kind of interaction event explanation was invoked for lives in a global cluster. So that would make more sense. But yeah. So I agree. It has a lot of problems with interpretation.
We have time for one more question. No question?
Yeah. There are a ton of HST observations of NGT 300, and this source is so lucky that falls off every each one of those. So I think. Thanks.
Okay, thank you again, Andrea.
While you set up, yeah.
Our next speaker is Marcella Brusa. Please correct me if I'm pronouncing your name wrong.
Marcella.
Marcella. She's an associate professor at Università di Bologna since 2019, but she has been there since 2012 after 8 years of postdoc research experience at the Max Planck Institute. Her research interests are in the field of extragalactic astrophysics, and in particular on the study of physical and evolutive properties of AGN through multi-wavelength surveys and on the feedback effects of AGN on galaxies. She has been involved in several national and international research projects, such as Cosmos, Zero Zeta, Athena. And she has also been a frequent visitor of the CFA in the years 2007 to 2009, working on C Cosmos data. And she's about to become a full professor at University of Bologna. So welcome. She'll talk about the multi-phase nature of AGN outflows from the launching region to the host galaxy.
Thanks a lot, Anna, and thanks. I really want to thank the organizer and Antonella for giving me the opportunity to be back here after so many years and present the results on the topic of multi-phase nature of AGN outflows, mostly done with the help and with the great work of the collaborators there. So let me see if I'm able to switch on. Okay, so the big question we really want to answer is the one on the top of this slide: how to suppress star formation in massive galaxies. We know for several reasons that this is really needed in order to understand fully the evolution of AGN and galaxies in the universe. So there may be a combination of different causes and mechanisms that may bring the suppression of star formation in massive galaxies, and I want to focus today only on the mechanism and causes that involve black holes, so AGN and black hole activity, and in different flavors. In fact, you may help suppressing star formation through two main different channels, let's say, by ejecting the cold gas, that is the one that is available to form stars, or just introducing turbulence and heating the ISM to different mechanisms, even involving jets in some cases. So there is this too big scenario to tackle this issue when we speak about black hole feedback. And in the following, I will mostly focus on the ejecting mechanism. So the one that involves the presence of fast winds that in fact remove the gas from the galaxy. And do we have observational evidences of this such black hole winds? Well, first of all, let's ask what we expect that this process is about, and then we see if we have these evidences indeed. So the expectation is that the winds may propagate from the very central region of the AGN, so in fact from the accretion disk itself, up to the full host galaxy, up to kiloparsec and tens of kiloparsec scale. This is a combination of cartoons of the different regions, from the very inner region up to, as I said, the full host galaxy. In a comment paper on Nature Astronomy, we put together years ago with Claudia Ciccone. And the main questions that we want to answer is: do we see this the presence of these winds, and most important, can we relate them to energy propagation or momentum propagation? Can we relate them on the mechanism through which they propagate through the host galaxy? So yes, the first answer, the first let's say take-home message is that we indeed see this the presence of this fast gas and fast perturbed gas that may trace the presence of the winds we're looking for, and we see them in as utilizing spectroscopy at different wavelengths and at different with different instruments, of course. We see them basically on space in the very inner accretion disk phase. We'll come in a moment on that. In the cold and neutral gas molecular phase, and we mostly are able even to spatially resolve them in the very in the ionized gas phase. So the tracer for these winds is the presence of bronze and or blue shifted components in absorption, like here, or emission lines, like asymmetric line widths. So I want to present a couple of well, okay. So one of the main topic we want to address is also what is the launching mechanism. I think there will be a lot of new results. Well, we hope at least for the local sample in the upcoming prism data, because of the information of the velocity of these components is very critical. But there are, I would say, again, two big scenarios. One involving mostly magneto-aerodynamic winds, and the other one involving radically driven winds driven by radiation pressure. And I cannot help to show here one of the seminal plots back again in the year 2000, proposed by Martin for the quasar structure. And the bottom line here is that whenever there are some winds that originate from the accretion disk, closer up to farther away, of course, if you intercept the line of these winds, you see these very fast velocities in the components. So as I said, I will focus on two topics or two results obtained by my group, and are tackling the accretion disk winds and ionized winds. All the other I'm happy to discuss later on if you want to stop by to have a chat with me. I'm here until 5 p.m. in the afternoon. So, as I said, well, in fact, the discovery of the accretion disk winds as ultra-fast outflows, as they are termed, referred to, go back to Chandra data of 20 years ago. This was a paper by George Chartas. These are much better and higher statistical data on local quasar like PDS 456 based on XMM Newton and Newstar data. And again, when you have all these very high quality data, you can fully fit even the P-Signi profile, and you can recover all the information that is carried by these absorption features, like the velocity of the wind, the mass included from the line flux, and the energetic and the mass outflow rate. So this was one key case. Later on, after they've been discovered, there have been a lot of statistical studies, mainly in the local universe, to assess the detection fraction. So how common were these kind of features in HN samples, and the seminal work here, the one by Tombe et al. In 2010, of a detection fraction of the order of 35%, and also the demonstration that, in fact, if we have very good, and this is the key point here, if you have very good statistics in the X-ray, you may also be able to relate and to study in very much detail the UFOs with other phenomena you see at lower energies, like the warm absorber. I forgot to say before, but the ultrafast outflows are best treated by the iron K alpha line in absorption. Sorry, that was needed to clarify. So what we decided to do, we had a very good handling, thanks to the Tombesi work on the low redshift, low luminosity regime. You see here are the counts that you need in the 4 to 10 kV band to do the proper spectral analysis. And so we decided to do almost the same, or hope to do the same also in a fully explored range of volumetric luminosity and redshift. And so we proposed back a few years ago one of these XMM large program called Subways, supermassive black hole in the X-rays, And all the work on this has been done by Gabi Mazzeo, my postdoc at University of Bologna. So, well, first of all, we selected sources for which we had already an idea of the number of counts from previous low exposure XMM observation. We tuned our new XMM exposure to be long enough to get the statistics of counts of the order of 10,000 to detect the outflow features. This was, I think it proved to be quite successful. This is an example of how we analyze the data when mixing up, and there are a lot of details in his paper. So here are confidence contours of an absorption feature at around 8 kV. It's in there. And this is an example of one of our significant detection. So at the end, we recovered a similar fraction. This is the UFO detection fraction versus redshift. This is subways, this is Tombesi, and that one at high redshift larger than 1 is the upper limit that we have from not dedicated observations and mostly from lensed quasars at higher redshift. So the detection rate is consistent with local values, and the main unknowns so far are all of those listed here. We can get something on which is the main driver of the launching mechanism by trying to understand or interpret the correlation that we see between the outflow velocity and the volumetric luminosity of our sources. We can focus on the panel on the right. This is again the local sample in blue, our subway sample in red, and the higher shift sample. You see there is a correlation. There is a correlation with outflow and luminosity, even if you just tackle one single source at different luminosity state, like PDF 456, that also has been observed a lot of time. And a correlation is naturally expected in a relatively driven wind by definition, almost. The expected slope is higher than the one that we measure, and this may be interpreted either as an effect of over-ionization at high luminosity. So this brings lower detectabilities of the features that we're looking for, or of course some combination also of some MHD processes in place. Again, here the most important point is that this is a subject, especially disentangle the two, that is quite challenging with current CCD detectors. And what we really need here is the high resolution spectroscopy. So the second part, I want just to say a few words on the work we have been done, starting from the Rosita catalogs, on selecting these agents of feedback. So far, instead of moving in the relatively low redshift, we try to go to search and to devise efficient methods to select objects that are expected to show these winds going at high redshift. So what's the rationale here? Of course, if you want to select agents of feedbacks in the two different classes, ejective or salvation mode, let's say, you should follow two different, let's say, approaches. And for the one we're interested today, you should expect the wind to be most active and most important, most powerful, in fact, in sources that are undergoing a merger phase or right after the merger phase, are luminosity sources, and they are also obscured, dusty, because the environment is pretty much a mess in these particular cases. So if you are doing this at redshift, you also maximize the fact to get these the galaxies in this phase. This is not that the Hopkins scenario for the quasars in the blowout phase. So another slide from the model part, let's say, to understand why the luminous feedback phase must be dusty. These are simulations by Tiago Costa and collaborators. So if you really want to augment the momentum and transfer the energy through this, let's say, radiation and driven processes, you you really want that your environment is pretty much dusty and optically thick, especially in the infrared. In this way, the photon can impart the momentum on the gas several times rather than just one time if the gas is instead optically thin. So almost naturally, you are able to start to accelerate. These are the maximum velocity you are able to obtain your gas as a function of your volumetric luminosity, that is the one that is driven your feedback, and you are able to obtain very high velocities like those that are seen in the outflows of the order of 1,000 to 2,000 kilometers per second, even at much lower volumetric luminosities in the case of multi-scattering. This is the red curves here, while for the one single scattering, you need basically a realistic, very high volumetric luminosity in order to have very high velocities. And this has been confirmed in many years. I've worked I worked for several years on detecting and showing this, that this hypothesis is more or less right. Many of the sources that we see at Redshift 2, very luminous, are indeed very red, and they show this very broad profile in the oxygen tree line. Oxygen tree line is one of the best because it's coming from the galaxies, not from the borderline region, so you do not have problems in assessing the contribution of the borderline region there. So what we did, given that we have some very good expectation of how these objects should look like, and given that these broad phases are expected to be pretty much short, so these sources are rare, the best is to go to look for them in large area X-ray surveys, because we indeed expect that this phase is also X-ray active with respect to that. So Rosetta is the first telescope able to provide a really sensitive all-sky survey in the all-sky survey. Much more sensitive than Rosat, and this is a perfect case then for Rosetta or Sky survey multivariate follow-up. We tested this with a pilot project starting from the X-ray selected catalog from the IFETS field that was one of the Rosetta data early data release field released by the German team a couple of years ago. We employed one method we tested in Cosmos, and we had 3 candidates there. It's based on X-ray to optical to near-infrared colors, and the only one, the star one was the only one with the spectrum we already had from Sloan, and in fact, we demonstrated that these are merging mass environments, red source of course, X-ray type 2 quasars with column density, relevant column density, and the O3 line, as you can see here, is pretty much broad, is larger than 1,500 kilometers per second. So what the main message here is that these objects are not known, they are not unique, they've been already known. In fact, this same source was already present in several all-sky catalogs that were put there, but it got unnoticed for this particular let's say relevance in as agent of feedback, until we tried to rediscover it with a dedicated approach through X-ray observations. And what we added, the final two slides, is that now we enlarged, we did the same project, not on a pilot sample, but on the full soft X-ray selected sources again from IFETS. It's more almost 12,000 sources. This is the work done by Lessing Musimenta, and the paper was in archive last week. If you are interested, there is a lot of information, and let's say the improvement with respect to the previous work was to use not one criterion but 5 altogether, are all of these diagnostic criteria or selection criteria for objects in the feedback phase. Basically, all the red sources there are our candidates. Blessing did a very great work on trying to compare all the different selection criteria and figure out which is the one that works best, and these are spectra for the subsample at redshift lower than 1, for which we could sample the orthogonal line, and again the combination of these criteria is pretty much efficient in selecting these, I mean, very sources with these very broad lines. Okay, I think I am done. We revised the only final point. We revised the combination of volumetric we revised the plot on volumetric luminosity versus wind velocity that was previously proposed in the literature. This was the correlation that was in place in the past, and by the work of Fiore et al. And with our new work, we find that the correlation is flatter, considerably flatter. I would say almost weaker and probably not that significant, for sure not that significant as before. And this already highlights the importance of sample selection and the importance of adding in this picture also X-ray selected sources that were basically missing in the previous work. And I'm done here with my take-home messages with some summary of the results and some slides to motivation for the future that is in fact the present. Thanks a lot. And sorry for being a bit long, but not that much.
Questions? Any questions?
I went too fast, probably.
Well, I have a question. You showed one of the spectra from the subways project.
Yes. I have others also to show probably. Yes.
Yeah, so were you able to identify what's happening to the left of the iron alpha?
To the left? What do you mean?
Up
Here?
in the upper, yeah, in the upper panel. So we have some like emission between 5 and 6, maybe.
This is 6 to 7.
No.
Okay. You mean 5 to 6? Maybe?
Yeah, right there.
Up there. I mean, here these are a ratio of with the best fit model of the continuum. So I mean, this should be consistent with being continuum. These are not really significant. If you are talking about this feature you see here,
yeah,
yes, these are overall not really significant in our methodology of definition of the significance of these sources.
Were you able to measure?
Yeah, I mean, otherwise you would have seen here some contours of similar to this one of the difference of your fit when you include an extra line. So this contours below is how your fit improve when you add emission lines or absorption line at these energies. Okay, so if you don't see anything here as significant as this one, it means that it does not improve the fit. So the lines are not significant.
Okay.
On the next slide, I've forgotten about it. So you said,
This one?
You had, there we go. On the right, you were saying that the blue lines are a good fit.
So the blue line is the fit of the entire sample. Okay. And this includes the local sample, middle redshift, and the redshift.
It looks more like it's steeper than that with just a few outliers.
Yeah. So you may speak with George, Charles us a lot, and also with Gabi. We discussed a lot the meaning and the significance of this fit. It's true that if you remove the redshift part, all the redshift 2 objects that are basically all these black dots here, there is no correlation almost at all. So these black dots drive for sure the correlation.
the very high luminosity ones that seem to drive it, and then it drops
This is
out.
just one source, by the way. This is just APM seen in different states. Yes, so it, APM 08279.
Oh, one source.
Yeah. And yeah, I think in the paper we have also the fit without including APM, just to.
I'm basically thinking that the slope of 0.5 might actually work quite well.
Without including the.
It's strong to say you've ruled out radiatively driven winds on that.
No. In fact, in our paper, we didn't rule out at all. Of course, it's still the best explanation. I agree with you that we had all the caveats in the paper. If you wanna have a look, we can have a look together later. But I agree with you that well, probably the referee was very much instead asking to put also an interpretation in terms of MHD or different interpretation than relatively driven, and we put some caveat sentences on that as well.
But also, sorry, the Venn diagram, once you get to velocity, you have like the speed of light. I think this thing is not fast enough. So
Yeah, that's true. That's true. That's very. And by the way, the correlation was is flatter in any case than the one that was previously proposed by, again, in the paper by Francisco in 2017. I don't mention here, but here the red points are and those based on UFOs and Mal wavelengths, Mal velocities, let's say, and UFOs. You see the UFOs were very, very few at that point, and so this correlation now is pretty much high. I mean, it's more solid than it was many years ago.
Any other questions?
On the slide, what do you think? Like the products is.
Yeah, so thanks for these questions. So I can comment on this figure that I skip. This is before we had velocities versus volumetric luminosity, or the other way around. I can't remember. It was volumetric luminosities versus velocity. Now we have mass of flow rate versus volumetric luminosity. So the mass of flow rate gives the X information of how massive and how energetic is the wind, not only in terms of the kinematics, but also of the dynamics. I mean, the mass that is carrying out. And what is was surprising us is that while in the velocity volumetric correlation, we found completely different trends. Here instead, we found our best fit is consistent with the previous fits in the literature that were these two other lines. And this may be explained if the different selections, again, X-ray selection and the infrared selection that were the most used before, were sampling objects in different phases of these outflows. The X-ray may be the faster one, but again with less centrated mass, so the first one phase of the winds, while the other selection maybe the lowest velocity in terms of mass, but with much more entrained mass, so the later phases of the wind. So the discrepancies can be explained in this way, and this is a way of adding an extra axis to an extra information to the figure before.
Well, thank you. That was an amazing talk.
Thank you.
And I think we have lots of open slots to meet with Marcella if anyone is interested in discuss further. So I think Federico sent the timesheet doing with the email, so you can just check.
I don't know where I can be seated, but I will figure out probably.
Yeah,
I don't know if it is.
You are here for the rest of the day,
Yes.
right? So
Okay.
thank
Thanks
you
a lot.
again.